How is everyone doing today?
Doing good?
Good. How about you?
All right. There we go. All right, so we are in the last effectively week or a day or whatever of classes. So before we begin talking about today's topic, I would like to ask what day you would like to have your final on. Realistically, we could have it as early as Wednesday, but I would be more inclined to offer it either this Friday, which would be the 26th, or next Monday, which is March the 1st. Do you guys have any thoughts?
I did end up having exams both of those days.
I would choose Friday, to be honest.
So we got one for Friday, one person saying they're having an exam both days. Later than Wednesday, March 1st or Friday. Okay.
Monday or Friday?
Monday or Friday. So far it seems like everybody is Monday or Friday except one person who actually definitively says Friday. Am I misreading the sentiment?
No, you definitely got that right. Friday is much better for me.
All right, well, I'm going to do Friday then. Largely, let's see what this last thing says. Monday, Friday, yeah. So we'll do Friday so that there's actually a little bit of time for you guys to work on the in-class portion of the exam, and you can use Monday to ask questions of me about the take-home tests and all that kind of stuff. So your final will be this Friday. All right, so then the last topics that we are going to cover are power in three-phase systems. We'll talk about instantaneous power and complex power today. If we have time, we'll talk about power factor correction. If not, we'll talk about power factor correction on Wednesday and then use the rest of that session as working a couple of example problems and or a review. So let's start then with instantaneous power in a three-phase system. So let's say that we have a Y-connected load, and we're going to be working with a balanced system as per usual. Here's our A phase, B phase, and C phase. Here's our neutral conductor. And so this would be some voltage VAN. This would be some voltage VBN. Here we would have some voltage VCN. And we would have a current IAN, IBN, and a current ICN. These six quantities are phasor domain, or specifically RMS phasor domain representation of sinusoidal voltages and currents. So I'm going to say that VAN of T, the voltage drop over the A phase of our load, has some magnitude Vm cosine omega t. And I'm going to actually, let me erase this. No, I can do it that way. It'll be a little bit more cumbersome, but that'll be okay. And the Bn of t is Vm cosine omega t plus theta v minus 120 degrees. The Cn of t is Vm cosine omega t plus theta v minus 240 degrees. And then I have my currents. All of these should be capital. Im cosine omega t plus theta I. I minus 120 degrees. And finally, ICN of t is Im cosine omega t plus theta I minus 240 degrees. So the total instantaneous power absorbed by this Y-connected load is simply the product of VAN times IAN plus VBN times IBN plus VCN times ICN of t. And we can use that trig identity that says the product of two cosine functions is 1/2 times cosine the sum of the angles plus 1/2 times cosine the difference of the angles. And what that will give us is 1/2 Vm Im cosine. Now I add the angles together, so that's twice omega t plus theta v plus theta I. Subtracting the angles, 1/2 Vm Im cosine theta v minus theta I plus, now I'm doing the VBN times IBN. So 1/2 Vm Im cosine twice omega t plus theta v plus theta I. And let's see, minus 120, minus 120, minus 240 degrees. Now I take the difference. So omega t minus omega t is 0. Then I'll have theta v minus theta I. Then I'll have negative 120 minus negative 120 is negative 120 plus 120. So I just get that term. And then finally, doing my C phase. Twice omega t plus theta I plus theta v plus theta I, but the order doesn't really matter there. Minus 480 degrees plus 1/2 Vm Im cosine theta v minus theta I. Now, as it turns out, this term, and this term are all sinusoidal functions separated by 120 degrees. It doesn't necessarily look like it, but we can treat negative 240 degrees as the same thing as positive 120 degrees. And we can treat negative 480 degrees the same thing as a negative 120 degrees, so that we have a phase angle of 0, positive 120, and negative 120. So they're all simply separated by 120 degrees. Well, when we add these three sinusoids together, like we've done previously, they all sum together to be 0. And so what we're left with is that the total power absorbed by a balanced three-phase load is 3/2 Vm Im cosine theta v minus theta I. And this is exactly equal to the average power absorbed by a three-phase load as well, because it represents a purely DC quantity. I believe very early on that I mentioned that one of the largest reasons that three-phase power is used here in the United States is because it gives a constant instantaneous power, which minimizes the vibrations in rotating electrical machinery. And we've mathematically proven that this is exactly what happens. Now, if we wanted to express this in terms of our RMS phasor voltages, we would see that this is 3 times, I'm going to call this VP IP cosine theta V minus theta I, where VP is simply the magnitude of our phase voltage, VAN, and IP is the magnitude of our phase current, IAN. Okay. Another way that this is often expressed, this is going to lead us to something real quick here, is 3 VP IP angle theta Z. So it's simply 3 times the magnitude of the voltage drop over one phase times the magnitude of the current flowing through one phase with an angle of whatever the impedance has. We know that the power factor angle theta S is the exact same thing as the angle theta Z. The only thing that we really have to pay attention to here, well, I guess it doesn't matter because all of them are equal. I was going to say it's the angle of one phase, but they're all have an identical angle, so that's fine there. Now, one thing that is interesting is that in a Y-connected system, like so, what's the relationship between the line currents and the phase currents?
I mean, without wires, they're equal.
Well, because, sorry. So the line currents and the phase currents in a Y-connected load have to be identical because the Y-connected load is in series with the transmission lines, right? So if we have some impedance ZW right here, ZY looks in phase, or excuse me, in series with that, and if we propagated that same ZW around all 3 phases of the transmission line, excuse me, we would see that for the Y-connected load, the line currents and the phase currents are identical. However, there is a, so the phase voltages and the line voltages are not the same. Instead, the line voltages are simply, from a magnitude perspective, the phase voltages multiplied by a factor of the square root of 3. And so we can get yet another definition for complex power now. So just to be clear, this guy is our complex power. We can have root 3 VL IL angle theta Z. This is also a valid expression for the complex power in a three-phase system where VL would be the magnitude of a line voltage like VAB, and IL would be the magnitude of a line current like IAA. And this is where the distinction of using theta Z becomes very, very important. So in a Y-connected load, we can't, if we wanted to use the line relationships, this does not take into account that VAB has a shift of plus 30 degrees taken into it. So that's why it's purely just using the magnitudes. So we have two expressions now for the complex power absorbed by a three-phase load in terms of phase voltages, phase quantities, and line quantities. They were effectively derived for a Y load, but they are also equally applicable for a delta connected load. So we could also go with a fundamental relationship like what we did in our analysis of single phase circuits. So if we didn't have these generic quantities like the magnitude of the phase voltage, the magnitude of the phase current, magnitude of the line voltage, or magnitude of the line current, we could also finally write this as 3 V I conjugate, where I'm going to put an A here, meaning the voltage drop over the A phase of the load. I guess I can do AN and AN times the complex conjugate of the current through the A phase of the load, because the complex power absorbed by each phase is going to be identical. So we only need to look at one single phase. So these three relationships all give us complex power. Oops. And we can simply use our single phase definitions for apparent power, reactive power, and average power from this. So the average power is simply the real portion of the complex power. The reactive power is the imaginary portion of the complex power, and the apparent power is the magnitude of the complex power. So to summarize those guys, let's do our average power relationships. We'll have 3 VP IP cosine theta Z, root 3 VL IL cosine theta Z, or for our reactive power, we have 3 VP IP sine theta Z is the same as 3 VL IL sine theta Z is the same as 3 magnitude of VAN, magnitude of IAN, sine theta Z. Finally, apparent power over here. Three VP IP or root 3 VL IL, and I'm not going to bother doing the 3 VAN, magnitude of VAN, magnitude of IAN, because that is the exact same thing as 3 VP IP. So here are our other complex power relationships. So if you understood the complex power relationships in a single phase circuit, this should be extraordinarily trivial, because you're just saying, well, now I have 3 identical loads, so I just add them all together. All right, so anybody have any questions with regards to these complex power relationships? If not, give me just a moment and I'll pull up an example problem from an old textbook and we'll take a look at it. Let's see, which textbook do I want to look at? Alexander and Sadiku seems good. I think page 547, yeah. All right. So let's say that we have a balanced 3-phase source. And let's see, how do I want to put this? I'm trying to decide whether or not I want to do a generic load or an actual impedance here. Let's start with an actual impedance. And I'm going to say that ZW is let's see, 1 plus J 0.2 ohms. Z delta is equal to 10 plus J 8 ohms. And let's say that I know the magnitude of my line voltage VAB to be 380 volts RMS. My goal is to figure out the power factor at which the source applies power. So just based on this small amount of information, and notice here, I have drawn a generic three-phase source. So we honestly have no clue whether or not it is a Y-connected source or a delta-connected source. We don't know what's going on internal to it. We should have enough information to determine the power factor at which the source is supplying power. So for example, let's see here. We have over on the right-hand side a load. In the middle, we have our transmission line system. Over here on the left-hand side is our source. And so it stands to reason to me that the complex power absorbed by the source, three-phase, will be, the complex power absorbed by our transmission line system, three-phase, plus the complex power absorbed by our load as a three-phase system. So which of these quantities can we currently figure out based on the information that we know?
You figure out the phase current through AB.
Okay, so we can figure out the phase current through AB. So IP, we can only determine the magnitude, right? Because that's all we have right now. So the magnitude of our phase current is going to be the magnitude of our line voltage divided by let me think about this real quick. The magnitude of my impedance, I think, right?
Yeah, it should be Z delta, right?
Yeah, I'm trying to decide whether or not I want to just assume a phase angle of 0 or if I want to work purely in magnitudes here to make our life easier or more complex. I'm just thinking about this just real quick here. But this should work. Effectively, what I'm basing this on is that impedance, by definition, is the ratio of the phasor voltage divided by the phasor current, which is going to be the magnitude of the phasor voltage divided by the magnitude of the phasor current with some phase angle theta z, which is just the magnitude of z with an angle of theta z. So I believe then that this should work perfectly. So we're going to have 380 volts RMS divided by the square root of 100 plus 8 times 8 is 64. So somebody with a calculator tell me what 300 divided by the square root of 164 is.
29.67301.
29.67301 amps RMS. So from this, S load 3-phase. Let's see. Yeah. Is going to be 3 times 380 volts RMS times 29.67301 amps RMS with a phase angle of inverse tangent 8/10. Somebody tell me what that is going to be. Let's start with a magnitude.
$33,827.22.
33.827. Let's do it kVA. What's my angle going to be?
$38.66 degrees.
38.66 degrees. All right. So that is the complex power absorbed by my load. Able to get that purely working in magnitudes, except for pulling my phase angle from the angle of the impedance. So for my wire, how do you think I can go about getting the complex power absorbed by my wire?
You have the current times the impedance to get the voltage. Once we have the voltage, solve the same.
So yes and no. So we're running into the issue here again where we're dealing with magnitudes. So let's, I'm going to do this as a quick aside here, right? So here's my transmission line impedance. I have some current, line current IAA flowing in, and there is some voltage VAA across it. So on a single phase level, the complex power absorbed by my wire, go away thing, SW is going to be VAA times IAA conjugate. But using Ohm's law, we can wind up writing this as the magnitude of IAA squared times ZW. And the reason why this works better is because I don't have to fuss with a voltage or current whose phase angle I don't know. I can work purely in magnitudes. I believe we used this relationship a couple of times when we were dealing with our just simple steady state sinusoidal circuit analysis relationships. So I would argue that the total complex power absorbed by our 3 wires is 3 times our current. So now we have a little bit of an issue here, okay? We know this current, it has a particular magnitude. And we know, sorry, that should be B. The magnitude C sorry, of this guy right here. But what we need is the magnitude of this line current. Can anybody tell me what I need to do to get that?
When did we get the current through CA?
So we don't know the phase angle of the current through CA, but because this is a balanced three-phase system, if we know the magnitude of the line current through AB, then we have to know the magnitude of the line current through CA.
Yep, you're right. I forgot about that.
So this is very similar to some of the example problems that we worked in class last Friday, right? We did Kirchhoff's current law and all that kind of stuff, and we figured out. So I don't know what the exact phase angle of AB is, but I do know for sure that CA is lagging it by 240 degrees. And so we developed a relationship that said effectively, IAA was IAB times root 3 angle negative 30 degrees. I think this popped up in 2 of our 3 examples that we worked on Friday. This is our conversion for line currents to phase currents and vice versa. Since we're only dealing with magnitudes here, we're just going to put in root 3, 29.67301 amps RMS. This root 3 relationship between our line currents and phase currents in a delta connected load is exactly why these relationships where we have 3 for phases and root 3 for lines work in in delta connected loads and Y connected loads. So this root 3 right here is converting my phase current to a line current. There are 3 total line currents. So I square this guy, and then I'm going to multiply by the impedance of my wire. And somebody tell me what number that gives me in polar coordinates, please.
.081 kilo.
I'm sorry, could you repeat that?
8,081.3 angle 11.3099.
11.3099.
All right, so 3-1.
KVA. All right, so we have quite a bit of losses here in our transmission line, but that makes sense because the impedance of the transmission line is fairly large in comparison to the impedance of our delta connected load. So that all seems okay. So finally, the complex power absorbed by our source is simply those 2 numbers added together. the 33.827 angle 38.66 kVA added to 8.081 angle 11.310 kVA. I wish I had remembered to pack a calculator when I was leaving my office a week and a half ago or whenever it was.
41.172 angle 33.8486 kilovolt amperes.
All right, so 41.172 angle 33.845 degrees kVA. So finally then our power factor must be what? Cosine of 33.845 degrees, which based on the angle, I'm guessing is somewhere around 70%. No, I take that back. It should be greater than 80% because the angle is smaller. So probably
83.
83. Is it leading or lagging?
Leading.
Is the angle positive or negative?
Yeah, it should be lagging.
Yeah, so if the angle's positive, it should be lagging. All right, so honestly, that was a fairly difficult example problem in as much as you were given extraordinarily little information and we were able to work our way through just using our simple three-phase relationships and understanding what it means to have a three-phase balanced system. So with regard to a power question, this is really kind of as hard as it could possibly get. So we got 30 minutes left, so let's take that time to look at our last topic, which is power factor correction in a three-phase system. So this follows power factor correction in a single-phase system almost exactly, except that there is one very important distinction. So let's say that I have a balanced three-phase system containing a balanced three-phase source connected to a balanced three-phase load. And for now, we will ignore transmission line impedances because they're just going to make math annoying. So in a single phase system, we corrected power factor by placing a capacitor between the terminals of our single phase sources. Well, in a three-phase system, we're going to do the same thing, except we're going to place a capacitor, identical capacitors in between all of the phases. So that might look something like this. where we have our delta connected way to do it, or if I have a neutral conductor available, it might look something like this. Where this is my Y-connected capacitor bank. Okay, so we have two different options. Typically speaking, you'll use a delta-connected capacitor bank because the size of the capacitors will be smaller and therefore cheaper. But they also have to be rated for a larger voltage. So there are trade-offs. There may be some special situations to where you would use a Y-connected capacitor bank because getting capacitors rated for that larger voltage may be prohibitively expensive or something like that. You do have two options technically, but in practice, the overwhelming majority of the time, you would do everything in a three-phase delta capacitor bank. So our steps for basic power factor correction still hold. We need to calculate S old, and this can be done on a single phase or a three-phase basis. We need to calculate S new, also can be done on a single phase or three-phase basis. Thirdly, we need to determine the VARs supplied by our capacitor. And this can only be done on a single phase basis. I make this point because mathematically you could solve, like if you calculated the difference between S new and S old, you could apply the equation to get a capacitor value, but that would be that one capacitor correcting all three phases of the system, which isn't how this works, right? There are three capacitors, each correcting the power factor of one phase. So that's why step 3 has to be done on a single phase basis. And finally, step 4 is calculate the value of C using the relationship C is equal to negative Q cap single phase divided by omega times the RMS voltage across the capacitor squared. So the magnitude of the RMS voltage across the capacitor squared. Now this is where things get interesting. This guy right here because the voltage is different if you have a delta connected system, delta connected capacitor bank, or a Y connected capacitor bank. And so let's see exactly what I mean by that by looking at an example problem. So let's say that we have a source, and it is feeding a load. Again, ignoring transmission line impedances just for the sake of making the math more simple. Capital A, lowercase b, capital B, C, capital C, N, capital N. And let's say that our load is absorbing in total, meaning over all three phases, 75 kW at 0.8 power factor lagging. And we want our new power factor to be 0.98 lagging. What value of capacitor would we use in a delta configuration, and what value of a capacitor would we use in a Y configuration? And we are told that the magnitude of the voltage VAB is 208 volts RMS at a frequency of 60 hertz. All right. So who can remember how to determine the complex power when you're only given average power and power factor?
Isn't it average power divided by your power factor times
Yep.
or the cosine of the power factor?
Absolutely right. So 75 kilowatts divided by 0.8 with an angle of inverse cosine 0.8. Do we want to do this on a single phase or a three-phase basis? It's entirely arbitrary. Just pick one and tell me what you want to do. All right, so nobody's saying anything, so I'm going to say that we're going to do it on a single phase basis. The only thing that we need to do to make this work as single phase is literally divide by 3, so that we will get the complex power absorbed by one phase of our three-phase load. Does that make sense? So instead of finding the total complex power, we now found it on a single phase relationship. So 75 divided by 2.4.
So 31.25, angle 36.87 degrees. And isn't it kilovars?
Yeah, kVA, so kilovolt amperes.
Right,
Because
kilovolt.
we're dealing with complex power. our new power factor, excuse me, our new complex power is going to be 75 kW divided by 3 times 0.98 with an inverse cosine of 0.98. Please tell me what that's going to give me.
$25.51, angle 11.48 degrees, kilovolt ampere.
Alrighty. And now that we have done these both on a single phase basis, step 3 will automatically be done on a single phase basis as well. So Q cap, the reactive power that is going to be absorbed by our capacitor, which is going to give us a negative value, is simply S new minus S old divided by J. So when you subtract those two numbers, it's going to give you some number with an angle of negative 90 degrees. At least it does on my calculator. So just tell me what the number is and put a negative sign in front of it. Don't worry about the angle.
Minus 13.714.
I'm sorry, could you repeat that?
Minus with 13.714.
Minus 13.714 k var. All right. So let's solve for the delta connected capacitance value first. So C delta is going to be negative 13.714 times 10 to the 3 volt amperes divided by omega. Since we're at a frequency of 60 hertz, this is going to be 120 pi per second. And now we need the voltage drop over the capacitor bank, right? So for the delta connected bank, that would be like we were putting it here and here and here. And we know that this voltage is 208. So the value of the RMS voltage that we are going to use is that 208 volts RMS. Square that, and please tell me what number you get.
$840.8 microfarads.
840.8 microfarads. Okay. So for our Y-connected capacitor bank, we're going to have the exact same thing. But here, we need our line to neutral voltage effectively, because we are connecting our capacitor bank from the transmission line to a neutral conductor. So how do I convert that 208 volt RMS line voltage, or line to line voltage, to a line to neutral voltage? So what I am asking is effectively this. I'm putting it this way so that you can see that it's something that we've done before on numerous occasions.
If you add the whatever the first term is in the subscript, like if it's v of ab, if you add v of ab plus v of b, you should get v of a. Maybe solve maybe.
I don't know, you're doing too much work. Let me explain what I mean by all this kind of stuff. All right, so we have it all down here. We have a Y connected system, right?
Right.
Okay. We know the magnitude, or excuse me, if we know the line voltage, so if VAB has some fixed value and we want to find that phase voltage, what do we need to do? We developed this conversion factor and have applied it probably 5 to 10 times at this point. So if you're given VAB, that is the same as VAN multiplied by √3 angle 30 degrees, right?
All right.
And we could go the other direction. So if we knew the phase voltage, we could get the line voltage by, sorry, if we know the line voltage, we get the phase voltage by multiplying by square root of 3 angle 30 degrees. Well, in this case, we know the line, we want the phase, so we have to divide by the square root of 3. Because we only need the magnitude, we only divide by square root of 3. So this would be 208 volts RMS divided by square root of 3. This quantity squared is going to give you a number, but over here as an aside, I want to show you something. We need to do that. Yeah, yeah. The Y-connected voltage is always going to, excuse me, the Y-connected capacitor value is always going to be exactly 3 times larger than the delta-connected capacitor value, because when you have that square root of 3 in the denominator of the denominator and square it, it's the exact same thing as multiplying by a factor of 3 in the numerator. So if we had 0.840 milli, that's going to be 2.520, I think. millisieverts for our Y connected capacitor.
Yep, it's 2.522.
Yep. So a little bit of rounding error because I didn't have in my head. But yeah. So that is the biggest thing if you're doing power factor correction to watch out for is that voltage drop over the capacitor, because it depends, what number you use depends on A, what you were given, and B, whether you want a line to line voltage if your capacitor is in a delta your capacitor bank is in a delta configuration, or if you want a line to neutral voltage if your capacitor bank is in a Y configuration. Other than that, it follows single phase power factor correction exactly. All right, so that is the last topic that I wanted to talk about for this class. I'm going to post a homework assignment on three-phase power relationships today. On Wednesday, what I would like us to do is go over, so there's going to be, I think, three-phase system homework assignments that will be up online at that point. I would like to spend Wednesday's class meeting going over any questions you may have about any of those homework assignments or any of this material that may seem confusing. It builds off of the single phase relationships that we dealt with in circuits 1 and again here in circuits 2, but I understand absolutely that it can be a little bit daunting to remember, when do I multiply by the square root of 3, when do I multiply by 3, when do I divide by the square root of 3, when do I divide by 3, etc. Am I going to have the YouTube videos up? Yes, I will work on posting those this afternoon, and I should have all of them up by at the absolute latest noon tomorrow. I've already started on them. I just need to get the 2 that I have edited, uploaded to YouTube, and then edit the rest of it. But yeah, I'll have them up by noon tomorrow at the absolute latest. Yep.
Do you
So,
mind
does that-
scroll? Sorry.
No, go ahead.
Do you mind scrolling up a little bit? I missed some stuff about power factor correction.
Not at all. Tell me when to stop.
Or that's good.
Okay. So these 4 steps are the exact same thing as you did in single phase power factor correction. It's just now steps 1 and 2 have the option of using 3-phase quantities. All right, so as I said, we're going to review on Wednesday. Ask me any homework related or 3-phase quantity related question you would like, and I'd be happy to answer any and everything you're willing to throw at. Hope you guys have a good rest of your day. Hope you've enjoyed this quarter. It's been awkward for me only having a handful of you guys. We've been able to get through some material actually rather quickly. I don't know. I hope I didn't confuse anybody too terribly.